So this is the class. In this class, we're gonna finish covering the Monte Carlo stuff. And in particular, what I wanted to tell you is how you do these calculations, which I think you might be doing in Quantum 2 at the same time. How do you do them with the computer? Okay, so let's start looking at this. Last class, we did the hydrogen Hamiltonian, right? And we ended up with something that where this energy depends on R and is given to us by this 1/2 alpha squared plus alpha over R minus 1 over R. So this is the, let me just double check that this is being displayed correctly. Okay, good. So this is the Hamiltonian that we will get for this, right? So after we have this Hamiltonian, I asked you guys, what would be the best alpha to choose for this to minimize it? And what was it? Alpha is equal to 1. Then we get that this E of L that depends on R actually doesn't even depend on R anymore, it's just 1/2. So if we look at it, what that means is that this guy, this equation right here that we're using, the exponential with alpha R, this is our variational trial wave function, right? With this alpha, with alpha being some constant that we can vary, that's our variational parameter. When you choose alpha is equal to 1, you get the exact solution because this value doesn't change anymore as a function of alpha. Questions? Yeah.
When you're saying exact solution, you're just saying that that's not adding independence in the parameter, not that it's the exact solution.
No, I mean that is the exact solution because as a function of a parameter, right? This one doesn't change anymore. I don't have a parameter for it. So if I was looking for the ground state, this is my ground state. So let's say you did the same thing and you said, I'm going to use a trial solution for this particle in the well. And I don't know what the solutions are, but I'm going to use signs. Then you find like, oh, look, this one minimizes everything, right? By chance, you chose sign, and then you did this analysis where you have the parameter, you figure out how do I minimize this energy, and you found that sign nkx, with nk taking on some values, is actually going to produce the ground state. So that's what we just did, except that we didn't know that this is a really good trial solution to try that will give us this answer. Or maybe I did, right? And I just didn't tell you. But that's to picture how it would be done as a calculation. Does that make sense? So this variational energy right here, we choose how to minimize it. And we know that this alpha R can be canceled if we put alpha is equal to 1. And then we end up with negative 1/2 1 squared. And at this point, we're like, hey, nice. This is not going to change with this parameter is equal to 1. It doesn't change. And that means that we have an exact solution. All right, so variational, so I'm just assuming, right? Because I haven't taught quantum. Variational is something that you have to see in quantum 1 or quantum 2. I don't know where you see it. No? You do perturbation. You just do perturbation. All right, so variational is this approach. So it's not perturbation theory because you don't have a perturbation, You don't have like, I have this solution and I'm gonna perturb it to this order with some constants parameters, right? We're doing where we're having this parameter and we're gonna vary this parameter. Are you guys familiar with superconductivity? So in the 50s, somebody came up with a theory of superconductivity. It was complete baloney, but it turns out that he discovered the Higgs boson, except it's not called the Anderson-Higgs boson. Dr. Babu says that it's because Anderson didn't take into account relativity. I think that they're just jelly of condensed matter. Are you complaining?
Actually, no. But actually, Anderson is the one who found out, and that Goldstone mode he found out, that was the real the Goldstone mode that is supposed to. Higgs original paper lacked that particle, and when referee reviewed that, he sent him back. Hey, there is something missing. You should go back and check. Then he was just lucky, but the real hero in that case was actually Anderson.
Yeah, so the Anderson approach for superconductivity didn't work. And a lot of people were working on the superconductivity issues. One of them was Bardeen. Bardeen had already discovered the transistor in the 40s. And he was one of the guys who got the Nobel Prize for discovering how transistors work, right? The work in the transistors, they gave the Nobel Prize to 3 people. Turns out that there were 3 people working in Bell Labs figuring out how a transistor works. When their boss realized that they were really close to making a transistor, he decided to make his own transistor, and he also gets the Nobel Prize. Turns out that he was racist too, and people don't like him anymore, but he was a horrible person. Bardeen is one of the team that was doing the work, and so this guy on top, the boss of the team, comes out with his own transistor, different from his team. He gets a Nobel Prize. Then this group, 2 people get the Nobel Prize. One of them is Bardeen. After Bell Labs, Bardeen goes to the University of Illinois. He's just working on different things. And at that point, he becomes interested in superconductivity in the 50s. By the early 60s, he has a theory of superconductivity that kind of works. He has his postdoc working on it. And he has his grad student working on it too. So it turns out that his grad student, and I don't know how much you guys know about superconductivity. Who knows superconductivity? You guys know what superconductors are? Yeah? You've seen one?
The only thing I know, if it gets really cold, the resistance gets really low.
All right. So
they're like electrons that like come very close together to form Cooper pairs, which would be like those ones.
all right, so that's the thing. You just said it. So Leon Cooper was a grad student of Bardeen. And I don't know if it was Bardeen or the postdoc who told them, we're close to solving this. Now we just have to figure out if we can find a wave function that will give us bound electrons. So if you just put as your wave function, as a trial wave function, your signs and some parameters, you would minimize to some value and you would think like, okay, this is the best that I can start, that I have with this starting point of my signs. You could use something like exponentials like this and say, this is the wave function, the trial wave functions, let's minimize it and figure out what we can get with that. So it turns out that Leon Cooper, was working on these things. They gave him the problem, see if you find a better wave functions than what I find. And then he comes up with a wave function that actually, when it minimizes, has less energy for 2 electrons being there. And that's where Cooper pairs come out. So Cooper was a grad student when he discovered this, and he was taking this approach, variational minimization. Okay? So that's why he gets a Nobel Prize. So it's called the BCS theory, Bardeen, Cooper, and Schiffer. Schiffer went crazy and started racing his cars like 120 miles in Florida. I don't know if he killed somebody or not, but they took his license away. I think he was trying to drive when he was 92 or something like that. So this approach is really good because you figure out a starting wave function, and you might get really close to the ground state. And maybe you cannot even tell if this is the real ground state, but it might be below a threshold so that you have a really good idea of what's happening to the system, just like Bardeen, Cooper, and Schiffer did, and they found Cooper pairs. So let's continue working in this direction. Let's assume that we just with the same thing, but instead of finding the exact solution, let's just vary the whole thing, okay? So let's assume that we are not done. What happens if alpha is not equal to 1? Then you have the general variational energy. Is given to you by, and here's the variational energy. Is, what does this symbol means? Expectation value. And what that means is that you would do -1/2 alpha squared alpha minus 1, sorry, plus and then my function is this one, right? So this is my variable VR. So the expectation value that I want is really the expectation value. This is what I want to find the expectation value of. These are the constants that we know. So now what we need to do is figure out what is this 1/r expectation value. And we can do that. We can do the integrals that we talked about before. It goes from 0 to infinity in the dr, and it will have r squared 1/r. What goes here is the wave function, right? Twice. So this is the bracket, Dirac bracket, where the 1/r is bracketed by one function and one function, right? So we're doing that integral. We have the 1/r right here. This r squared is because and the 4 pi is because we're doing the rotational integral, right? And then we would have that there's e to the alpha r, e to the alpha r twice with a negative in there. So that's where we get the 2. And then on the bottom, I need to do the other component, the normalization of this. And this one is also an integral with dr. It has the 4 pi for rotational symmetry. And this is just the wave function, 2 alpha r dr. All right, so if you do this, you actually end up with alpha by itself. Okay. And what that means is that my variational energy, now with the parameter alpha in there, is the expectation value of this L energy. And we now have that there's an alpha here instead of 1/r.
Except for in the denominator, it should be 4 pi multiple r squared dr.
Yep, I missed the r square. Thanks. Yeah, it's the same integral, except you don't have the 1/r for this expectation value. Yeah. So we look at this one. We have the 1/2 right here, alpha minus 1, and then there's an alpha coming in here. So you can actually rewrite that as 1/2 alpha minus 2. Questions? So this is the expectation value of this r, right? We could also compute it. So this is an easy example, easy enough that you can do it by hand. But what we've been talking about is doing Monte Carlo to do integrals, right? So now what we can do is that we can also compute all of this by sampling and doing the following. 1/n. L goes from 1 to n. E L R of L. And then here, there's a set. This is our vector that we're sampling, right? This is the vector for the position of the hydrogen electron. And this is sampled for this wave function, the phi r squared. So that's how we could also calculate this integral by doing that calculation. So that's how we would get this expectation value. We could also calculate with numerically or by hand. We could calculate the variance and now that we know what the function looks like, right? What we would say is that the variance of this EL it's EL squared minus EL squared like that. So we could calculate this guy's too and obtain so this is the result if you do the calculation of those integrals, and you will get this. So this is just by itself the expectation value. This is the variance, which is the expectation value squared minus the original expectation value squared. And you can calculate those by hand and get those values. So now, if I know what my energy looks like and what the variance looks like, if you were doing this numerically, you could plot it out. And have your variational energy here as a function of the parameter that goes from 0, let's say, to 2 alpha. This is the variational energy. And you actually have that you can calculate it. You would go like that because he has this form. And then you can calculate the variance at every point. What is the variance at the point when alpha is equal to 1? Zero. Let's say that we move away from it. So you would come here, right? And it would be like this as your variance, and then you come here and it's this as your variance, right? And you can calculate that variance as you shift away from it. And it would look like that. And you can figure out this numerically too. And this is what you can do with the Monte Carlo method too. So you could do it by hand because this one is simple. Let's say you wanted to do something that was more complicated. Maybe you don't have access to, you don't have the solution per se. and your calculations will be harder, then you do it for the system numerically. So something that is interesting here, there's no fluctuations at this point. Why was that?
The mean.
Because that's the exact solution. So if you're in a problem, when you're in the exact solution, there's no fluctuations to the EL. I guess this is EL right here, not variation. No, wait, I might be wrong. Okay. It's one of the two, right? But basically there's no variation here because you're at the right point. So there's no error in energy. And you know that the trial wave function with alpha equal to 1 is the best one. So the other thing you can do, you minimize the variance in the energy, and then you get what is the best trial wave function. So you look, where is the variance the smallest? And sometimes it's not going to go to 0, right? Here it goes to 0 because that's the exact solution. You might be doing something numerically because you don't know what the trial wave function should be, but then you can look at what is the best trial wave function to get there. And it's not going to be perfect, but you can get the best that you can do by minimizing this variance in the energy.
Professor?
Yeah.
Is there any reason like in numerical solve, like we are looking at the variance, we could have just take the first derivative and set it to 0 and get the value for alpha, right?
Say that again?
Like we could have just took the derivative of the function, like we have alpha and alpha.
Oh yeah, this is one is an easy one, right? Like this is the toy problem to check how your intuition works. This one is good as a toy problem because it has that you can take the second derivative and figure out where it is.
So without taking variance,
Mhm.
was not it easier to take the first derivative and set it to 0? Because that will give us the, or is there any reason, like numerical reason for looking for the variance?
The reason to look for the variance in this case, I mean, we already knew that it was minimized right here, was just to visualize it. So when you're doing your numerical calculation, right? What you would get is that you would try different values of alpha, and then you would try, let me bring this back. Let's say you try 100 different vectors for this to do your integrals, and then you have different alphas, and you see that the solution has these error bars, and it's right here for this value of alpha. Then you do it for this value of alpha, and it has this error bars, and this value of alpha, and it has this error bars. So that's the solution that you're coming up with numerically, and it has those error bars. So that's your analytical solution would be in blue that you can get, and you know what the variance is and everything. But if you were doing it numerically, what you would get is not a function, but rather you would say at this alpha or this alpha, I get this as my mean energy, and I have this error bars because I had to do it 100 times.
So that's what I'm saying. So we get for any trial function, we get the energy alpha into alpha minus 2, right?
Mhm.
So we can take the derivative of alpha into alpha minus 2, and for different a, we are doing the same thing. For different a, we can check where it is 0. So that's the alpha where the first derivative is 0, right?
Mhm.
So that seems easier than that. So I was wondering if there is numerically any reason for any other problem taking derivative causes some problem, or
I think that this is the case that it becomes so easy because it's built like that. Yeah, there's no reason for it to work like that all the time. It's more like if you were doing things numerically, you would do this and get this red dot as your average, and then this is the energy that you calculated as these error bars and so forth. So yeah, that one is because it's an easy one to do like that. Both. I mean, there's a cost condition for the hydrogen electron, and it's really easy to get the right one. So What if you had a different problem? So let's say that you had to do a little bit more complicated function. In this case, the hydrogen. So the hydrogen atom is too simple. So what do we go with? The next step in the complexity, right? We make it the hydrogen molecular ion. So in this case, what we would have is that this is in position. Here's one position, here's another position. That's where our ion is. And then we would have that maybe our electron is here. So this distance right here is R right here. Let's say that the distance from here to here was R. So there's a vector going like this. Let's call this one R to the right. And then there's another one coming this way. Right here. Let's call this one R to the left. Okay. So you have a position of the, this is the hydrogen molecular ion. Right here. We have that the two protons are separated by a distance R. In the electron that is located here is located at position R, is R to the R away from this one and RL away from this one. So those would be our two vectors, right? Questions about this geometry?
This is like diatomic hydrogen gas.
Molecular ion, right? So you have a hydrogen molecule, but only one electron,
H plus.
H2 plus.
Yeah, 2 protons more.
Yep. Yeah, I mean, this is more complex than the previous one. But it doesn't have 2 electrons because that's more complicated.
Does this thing actually exist?
Yeah. You ionize a hydrogen molecule. Very easy. You had another question, Zach?
Yeah, I think it's just, I can't remember the basic chemistry. I thought hydrogen only had one proton, so wouldn't it be helium?
No, this is a molecule.
Two hydrogen.
Yeah.
Oh,
They're not.
Yeah.
okay.
2 hydrogen, a molecular hydrogen is H2. Yeah. All right, so just for geometry case, this is my distance, the vector RL is R plus R over 2 like this. And then my vector R is this one minus R over 2. Okay. So the Hamiltonian we have a single electron, so it's a single particle Hamiltonian. So we have this term right here for the kinetic energy. Then we will have the distance from ion on the left. And then we will have the distance from the Coulomb interaction, right? With ion on the right. And then there's a term that is 1 over R right here. This term is the Coulomb repulsion between the nuclei. So this is the distance R. There's an ion proton here, there's a proton here. This part of the Hamiltonian is going to be a constant, right? Because this distance doesn't change. The distance between the 2 hydrogen protons. And we can just drop it from our calculation because it's just a constant. Questions?
And the gradient here is with respect to smaller.
Yeah, just one electron, right? So that's your important particle. One electron. The ions, you don't take into account what they're doing because they're too big and
And also like there is gradient of capital R also, but it is also ignored.
it's
because
ignored
just
because the ions
Center
don't.
of mass is not
Yeah.
changing, so
This guy is 2,000 times heavier than, yeah. That's the assumption we're doing. Okay. So we ignore those terms, and now what we have is gonna be that this guy is our molecular orbital. Now, some definitions, this guy is a molecular orbital, and it's molecular because it's a function of two protons. And our trial wave function, we have to choose a trial wave function at this point for this. So any suggestions about what we choose?
it will be larger near the nucleus is both of these nucleuses.
It was Wonderwood's bond between them or,
No, it's Coulomb interaction.
yeah.
What did you say?
It should be symmetric, right? On the both axes.
Yeah, it
because
can be
both-
symmetric.
So
Yeah,
it's good to choose a symmetric function by hand in the
Yeah.
first place. And it will, attractive force will be largest when RL or RR goes to 0. So it can be that thing, so you can fix it. Or maybe just can take some Gaussian.
so you want a
Could be a
Gaussian,
possibility.
a Gaussian could be a possibility, right?
Yes. It is. a
But
good
we just
possibility.
figure out what is the proton.
So let's
electron.
take Gaussian with a modulus sign of X. So that negative and positive has the same effect on both of the sides.
Well, we just figure out that the exact solution for a proton electron pair is something, right?
It
What do we
require
put those two together?
Maybe one
Two raised to minus RL.
minus of this.
and multiply both of them.
So this is the solution for one. Now we're gonna put one on the left and one on the right. Because we already know that, wait, that one works for the other one, for the single proton, right? So this is our trial solution now. I mean, I could add more terms. If you wanted to, I could make it a Gaussian. But I didn't prepare my notes with a Gaussian. But since we know that this one works for the single proton, how about if we try this? And if what we're doing here is actually called the combination of the atomic orbitals to make a molecular orbital. So this is a quantum trick. We know that this works for one atom. Let's combine them together and see if they work for the molecule. Okay? Questions so far? No? So we start solving for this. And we have that the energy is given to us by this monster, right? I have my Hamiltonian up here. I have my wave functions here. I just have to do those two parts in there. So what this ends up being is, on the bottom, I just have this one and this one. What goes on the top? So I have to do this term right here. That's gonna bring down the alpha square. Then I have this term right here. This one. All right, so I'm putting this guy into my Hamiltonian, right? And operating on it, and then going step by step. So then what I wanna have is one of them right here. And then the other one which is the same thing, but with the R. And then the one this one I'm omitting. And just keep it like that.
But how did the sign change to negative? Positive?
So I brought it twice down, right? So I have this one half. So I brought it twice down, that's how it's half a square.
But for the second term in the Hamiltonian minus one over RL, when we apply that to the wave function. We just get a minus, we have to minus alpha RL over.
Maybe you're right. Maybe you're right. Because I'm bringing this one down twice and then the negative one half here. Then this one,
So how did we get another factor of alpha? Are we like doing a derivation? Like, are we taking the derivative? Or one over RL?
good questions. I just did it a while back, so I don't remember. That's what I wrote down on my notes. But let's continue like this. If there's a mistake, we'll see it later. At this point, we have this as our E of L, right? What happens if R of L goes to 0? Then we would get that there's a portion that goes like this, alpha RL e to the 1 over alpha RL. And then we have in the bottom this guy. RL goes to 0, will give me alpha RL 1 over 1 plus e to the negative alpha R. So if we do that, what we want at this point is to have alpha RL 1 plus e minus alpha capital R minus 1 over RL to be 0. So that's coming to the condition, the cusp condition that we had in the single proton case. So in the single proton case, we were getting this cusp condition for the function. If we set it up like this, we want to solve for this to find what is the cusp condition here. So that means that if we do that, alpha being equal to 1 plus e to the negative alpha R this is the cusp condition. If we did the same for R going to 0, we will get the same thing. So now what we're looking at this point is the following. Let me bring this over here. So for this Hamiltonian, right? If we go with R going to infinity. This guy, if we go with big R going to infinity, what do we end up with?
Just a molecule, hydrogen.
One atom, right?
One atom.
So Sarah, if we go with R going to zero, capital R going to zero, what do we end up with?
So there is just one proton and one neutron.
So this R goes to zero, right? So what happens to the two protons?
Oh, they will, what's that, reverse,
Yep, exactly.
and by the,
So you get helium, right?
Yeah.
The two protons coming together,
oh, yeah,
you get helium. So let's look at this condition. This is the condition that we have here. What happens when R goes to infinity?
We get our hydrogen back.
Alpha one, right? What happens when R goes to zero?
helium.
Alpha becomes two. So this is hydrogen. And if we have, no, wait. Let me fix this real quick. As R goes to zero, then we get alpha is equal to 2. And we have the solution for helium. So this is actually the right solution when we have helium, when we have hydrogen. Those are the exact solutions. When we're in this spectrum over here, that's the right solution when we have the two on top of each other. That's the helium one. That's the right solution when we only have one of them when alpha is equal to 1. So now we know that we have the right solution at the ends of the spectrum, a 1 and a 2. So now my favorite trick, what goes in the middle? Right? How do you bring them together? How do you get the rest of the thing? Does that make sense?
I didn't get your last one. That we should mix these two methods and.
No. What I'm saying is this is the condition of alpha. The value of alpha is going to be between 1 and 2. And we know that we have the right solution in the extreme case that you have hydrogen and the extreme case that you have helium, 2 protons. So then the question becomes, how does it behave as we go in between? So as we go in between, right? Then now you know that this R is not infinity and it's not 0. And now you have the right value. This trial wave function, where did I put it? Over here. This trial wave function right here, right, has an alpha parameter on it. And that alpha parameter is given to you by this value. So now if you set the distance between the two ions, now you know what your trial wave function is that is going to give you the ground state. So now you know it's 1 on this end, it's 2 on this end, and you have the R parameter to bring them to whatever value you need it to be. Okay? Questions? So this is variational, but it's not really variational because we're getting the right solutions for these problems. And these are easy because it's a single body system. Does this make sense? That's why we have exact solutions. It's just one electron in the system. It's like if you scatter and you only care about the solution on one of the guys, you don't care about what happened to the other body, right? Because you assume it doesn't exist. Yeah.
We can only find the ground states through this method, right?
You can only find the ground states.
Through this solution, like 2 or 2 got in, you only got one value, like, for example. wave function?
So this is the ground state for the single electron case. Your question is, can you find the excited states? If you have the solution for for the ground state in the single electron case, then what you can do is orthogonalize with respect to that guy, because your ground state is orthogonal to your first excited state. So whatever your wave function is, right? If your wave function, let me give you the simplest example. Here's your particle, right? This is your ground state solution. So now I have to find a function for my first excited state, has to have one node and has to be orthogonal to this guy. And then you can play and realize that this one does the trick. You can move the node around and figure out where is it that I can put the node so that this minimizes. And that's your first excited state. If you put the node right in the middle, you get that first excited state. If you move it to this end, the energy goes higher. You move it to this end, the energy goes higher. So this is how you would build it. If you know this one, you can build an approximation and then have a movement trial in there. And then if you want to go with the next excited state, it's going to have two nodes, right? So you can go like this. And this is orthogonal to this one, and this one is orthogonal to this one. But once you build one, you can build the right. Once you found the first one, you have a way to find the next ones. All right, so I said that this was the easiest one to do, and that's why we're able to do this variational without really doing variational. Does that make sense? How come I said, let's go with the most complex one up the ladder? And I didn't go with 2 electrons and 1 proton. Any ideas as to why? You have 2 coordinates to worry about. Doing things with 2 electrons is exponentially difficult as compared to 1 electron. If you're going to this 2 electron system, is way more complicated. So let me just write that down.
Because they have more freedom, I mean.
Yep.
Could we try to do that with like keeping the photons, like, so we could fix the electron and the photon around this, change our coordinate system that way?
No, because the protons are supermassive. That's why we were able to keep them static. So the approximation is that the mass of the proton is like 2,000 times the mass of the electron. So our approximation was protons don't move, and we don't care about the 1/r term. We don't care about the kinetic energy of the protons. In this case, you want to do that there's 2 electrons and 1 proton, then it becomes really complicated. You can also don't consider how the kinetic energy of the proton is, but now you have to deal about the Coulomb interaction between the 2 electrons.
But maybe he's asking like, what happens, suppose we looking from left, we go to and sit on top of electrons. So from that perspective, now proton is actually moving, right? Like,
Oh,
because-
okay, you could
but
do that.
that actually adds a lot of complication, because now we are in a accelerated reference frame, right? So there will be lots of forces.
Also,
Other
we only
external
set on one
forces, right?
electron, so the other electrons will also be moving around. We can only set on top of one of them. That's
Yeah, that's also really complicated. So if you're dealing with more than 1 electron, we need to obey Pauli's exclusion principle. Everybody knows what the exclusion principle says? Yeah. Yes? Yes. All right. So you have to obey Pauli's exclusion principle. What you would do then is that you build for 2 electrons, your wave function is not gonna be a complicated monster because now you have this multiplication factor right here. So this is like the summation. Sigma is sum, capital Pi is multiplication. And what we're doing now is that we would do the wave function is two bodies, and it has R1 and R2. And then you have to do the determinant of the single body wave functions. So this monster right here is a two-body wave function. And it's usually called the Jastrow two-body function. And then this one is the single body, one body wave function. And this whole thing right here is called the Slater determinant.
Why we use the determinant here?
Because you have to obey Pauli principle. And if you have two electrons,
Yeah, they can. It's one of them.
your wave function is very complicated because you have four fermions,
Mhm.
electrons are fermions. You have to do determinant in the two-body system is this wave function x times wave function y. No, x1, x2, particle R1, R2, and so forth, minus the other one. So you have to make sure that this guy and this guy are not the same orbital, occupying the same orbital,
Right.
unless they're different spin.
Mhm.
And at this point, we haven't even looked at spin. So this is the single particle wave functions that we just looked at could be your starting point. And then you build this Slater determinant with them. So if it's two electrons, it's a 2x2, it's a 2x2 determinant, and there's just two terms on it. If it's three electrons, now you have three multiplications, boom, 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 three of those terms. If it's four, and it just keeps growing like that. And then this two-body Jastrow is the thing that goes in front of that, that tells you a complicated monster of the two things. But if you wanted to do two electrons in a proton, that's the wave function that you start with, and then you start just putting the parameters in and trying to get them to work out. Okay? Questions? So this is something that you wouldn't see in quantum 1 or quantum 2, I'm pretty sure, or you saw it already.
I have a question. So why didn't we think of Pauli's exclusion principle when we brought the two hydrogen, the two protons together?
Because we would thought of them as classical particles. But you can put two protons close enough together so that they're forming the nuclei of the helium, right? We just assume that they're in different spin states. Yeah. Anything else? All right, so let's keep going. Let me check the time. All right. So, at this point, we could finish the class right now. Since there's people missing, I don't want them to miss too much and start a new topic. What do you guys say about that?
Yeah.
Yeah.
Sounds good.
All right, so let's stop the class right now. You guys have questions about this? No? Yes? So dealing with the multi-particle system is really complicated. In condensed matter physics, we have an approximation where we assume that everything works because we have a sea of particles. And then we just have a single particle on top of that sea of particles. And that is a single particle approximation so that we don't have to deal with a lot of this stuff. Now, there's people that work this out correctly. Usually it's nuclear physicists and some sadistic masochist condensed matter physicists. They call those few body physics. That's the most difficult problem to solve in all of physics. The few body problem. When you have to deal exactly with 3 electrons interacting, 5 electrons interacting, maybe even 9 electrons, or it doesn't even have to be electrons, right? It could be quarks, like in nuclear matter, quark gluon plasma. When you're dealing with, in some cases, when you're dealing with the particle physics, you might assume also it's a single particle and you're solving the quantum mechanics for single particles interacting. Or if you're a nuclear physicist, you might be thinking about this interaction of particles like the heavy elements that have a lot, like, let's say you had lead colliding with lead. Where's lead? Right there, 82, right? So now you're not dealing with a proton crashing with a proton in the CERN. You could be at Brookhaven where you see a silver ion and a gold ion crashing into each other. And now you have to deal with all of those interactions. So those problems are extremely hard. And one of the solutions is to solve it with a computer where you have this many protons, this many electrons, all of them treating them with Monte Carlo calculations to do the analysis. And you put like maybe a variational Monte Carlo approach or other approaches like that. So that's why Monte Carlo is used by a lot of physicists. So the hardest problem you can think of is solving this it's called either many body physics or few body physics, depending on whether you're condensed matter or you're a nuclear person, quantum mechanically. Okay, so let's finish here. Next week is Thanksgiving. Everybody knows that, right? We're not coming next week to class. So there's no class all of next week. Now, the other thing is that I was put into a committee is like, you guys know about the strategic planning? The university came out with a strategic plan. You guys heard of it? No? The president said it. It was announced a couple of weeks ago. So there's a strategic plan. For instance, one of the things is to become the best land grant institution in the US. And a bunch of different things that are put as like, these are what the university is going to focus on for the next, I don't know how many years, right? So unfortunately, I got put into an all-day committee on the Tuesday after Thanksgiving. So I won't be able to teach the class, but what I'll do is that I'll have a class ready for you guys on video. So I'll upload it on YouTube and or Canvas, whichever one is easier, and then give you guys access to a code that goes with that. Okay.
You ask us to like, share, and subscribe.
I don't think don't you need like hundreds of thousands of people to do that to start getting paid?
That's how we start with one and then you go to 100, then you start making more money.